Hi, my name is John Nemechek, and I'm here to show a simple spectroscope that can be used to look at spectra, both emission and absorption, to understand solar system and chemicals and the like. And the phenomena is using optical diffraction, and in this case we're using a simple transmission grating. So here I have the first order, or the zero order, and then the plus and minus first order. And we can use that in the construction of a simple spectroscope, which is made available from the Solar Center at Stanford University. And they're very generous in supplying these materials free of charge to educators, maybe just paying for the postage to ship these spectroscopes. So the simple construct of this is a slit with the transmission grating, and then inside is a small wavelength scale. And so using ordinary household lamps, we can look at something as simple as an incandescent bulb. And when we look at that with the spectroscope, we'll see a nice continuous spectra. I've also found a Home Depot and other hardware stores a simple incandescent bulb with a neodymium coating. And the bulb manufacturer did this to suppress the amount of yellow light and kind of boost the amount of blue and red to give it a cooler white appearance. But this bulb is very helpful for science because it takes that continuous spectra and gives very discrete absorption bands where the neodymium is absorbing the yellow light. And that's a terrific way to understand how we discovered a number of elements, including helium, in the atmosphere of the sun, using a simple device like this. So to complete the choice of spectra, we can look at a compact fluorescent light. And the fluorescent light has a trace amount of mercury in it, and the mercury will give rise to discrete emission spectra. And that's very helpful to understand things like Bohr's model of the atom, where electrons occupy a very discrete energy state, and when energy changes, let's say from a higher state to a lower state, it gives off a specific amount of energy, and that can be viewed as a very specific color for that element. Now we have a good example of a continuous spectrum. This is from a regular household incandescent bulb. So you can see the blue, the green, the yellow, the red, kind of all continuous. The next bulb we'll look at, it's also incandescent, but this one has a neodymium coating. So it may be a little difficult to see by camera, but instead of a continuous spectrum, what you may observe is an absence of some of the light in the yellow. And that's due to the neodymium taking up the yellow color. And so that's a great example of really what the sun looks like, and we can determine the presence of elements in our sun and other suns by the absence of certain lights that we can relate to certain elements. And then the final bulb we'll look at is a compact fluorescent. And so what this gives us is discrete emissions. So in this case, the fluorescent has a trace amount of mercury, and so for instance we can see a very clear green band, and that's the mercury E line, which is 546 nanometers. And so as we think about electron properties changing discrete energy states, we can relate how much energy is changed by the color of the photon given off proportional.